Hello, good afternoon, Dr. Suraya. My name is Hua, and today I'm going to present about my structural design project for this semester, which is for Group 2 and Section 1. For the project team member, which is including myself, has a project manager, and Lee Xingxian has a design manager, and Muhammad Afan has designer, and Putri Nurul Izora has sub-project team. So, moving to a project background, which is state that structural design is the methodological assessment of a structural strength, rigidity, and stability. The purpose of a building is to carry or sustain load if the structure is poorly planned or built, or if the actual applied load are greater than the design specification, the device is unlikely to perform as intended, which could have major consequences.
This is our design drawing. This is our rabbit design from back view and front view. And this also our rabbit design, but this is from left view and right view. This is our rabbit design from 3D view.
For moment distribution method, it has two, which the blue one indicates for continuous beam and the purple one indicates for simply supported beam. Moving on to the action of slab, the GK and QK is 5.75 kN per meter square and 3.0 kN per meter square respectively. For action of beam is GK is 11.409 kN per meter and QK is 5.5 kN per meter. For shear force diagram that we obtain, the maximum shear force is 35.48 kN, and for bending moment diagram is maximum is 26.61 kN meter. Based on the formula, this is all the values obtained for the slab action and the action of beam for span BC and span CD. Moving on to the initial part, the IXX obtained is 2286.33 multiplied by 10.6 mm4, and for the IYY we obtain is 247.4 multiplied by 10.6 mm4. So the biggest moment of inertia of IXX is chosen. For calculation case 1, we use moment distribution method to gain the values for span BC and span DC. You can see here is the shear force diagram and bending moment diagram result for the calculation of case 1. Moving on to the calculation case 2, the fixed end moment that we got is FEMBC is negative 86.94 kN meter, and the FEMCB will be the opposite value of the FEMC For FEMCD, we got negative 67.96 kN meter, and FEMDC is positive 67.96 kN meter. Here is all the reaction values for span BC and span CD. For calculation case 3, we did the same thing, which is find the fixed end moment for all the span, and we did the moment distribution method to get the end moment. All the reaction of span BC and span CD are obtained to be illustrated in the shear force diagram and the bending moment diagram. Lastly is the result shown for the envelope of SFD and BMD, which is the extreme maximum or minimum bound of all the result for that load effect at the point on the element for a given selection of load cases and load compilation.
This slide shows us specification about simply supported beam. So our sinom is 35 millimeter, and the rest is our bending moment diagram and shear force diagram. After the calculation we do, finally we get tension steel is 3H60 and compression steel is 3H12. The maximum spacing we get is has its 250. For our minimum links, we'll also get hash 6 500. Based on our deflection calculation, we can conclude allowable span effective is larger than actual, which means is acceptable. Our cracking is 74 millimeter, which is smaller than 118, which means acceptable. Here is detailing simply beam design.
This is a calculation of continuous beam. So here is information about our continuous beam. We can see that our C norm is getting 34 millimeter. So we estimate we get the 35 millimeter. This is a combination of shear force and bending moment for continuous beam. For span BC, we can see that the K bar is smaller than K. So we need to calculate the compression reinforcement. For span C double prime D, compression reinforcement also is required because K bar is smaller than K. Our bar size is smaller than maximum bar size, which is 200 millimeter. So 3H20 and 3H12 is acceptable. For fractural support, our K bar is smaller than K, so compression reinforcement is required. Same to fractural support span C prime to D, the K bar value is smaller than K, which means compression reinforcement is required. Both of the span, which is B to C prime and C prime to D, the check deflection is bigger than 4500, which means acceptable. Both of the span we use same of the size reinforcement, which is H6 to 1050. This is a detailing for continuous beam design.
Okay, next moving on to the one-way slab of simply supported. So with based on the Eurocode we will show in this presentation, as we can see here the GK and QK, which is 5.75 kilonewton per meter square and 3.0 kilonewton per meter square for the variable, which is QK. And for the slab thickness that we have got and chosen, which is that we have tried, is 175 millimeter. So the durability, fire and bond requirement, it was based on the Euro code that we have taken the value, and also based on our design also, and the action analysis that we have got for the new GK, which is 9.0 kilonewton per meter square, and the QK is still the same, have is 3.0 kN per meter square, by using the formula of design action that we have obtained, which is 16.65 kilonewton per meter, based on the Eurocode for the formula of design action. Okay, for the shear force and the bending moment, the shear force that we got is 29.14 kilonewton based on the formula, and the bending moment is 25.5 kilonewton per meter based on the formula also, and the effective, depth, which is 135 millimeter. So the design moment that we have obtained previously, which is MED, is equal to 25.5 kilonewton meter, and for the main bar that we have obtained, which is H8/100 503 millimeter square per m, and secondary bar, which is H8/200 251 millimeter square per m, and the calculation and the formula was based on the classes that we have learned during the structural analysis class. Okay, for the shear part, based on the design shear force from the previous calculation that we have obtained, which is 29.14 kilonewton, and based on the formula that we have learned during the classes that we got for the VRD, which is 64.8 kilonewton, and for the V minimum, which is 59.77 kilonewton, which is bigger than the V minimum, which this means is okay and suitable. For the deflection part, as you can see here, the actual is less than allowable, which means our value is okay. Because why? Because based on the formula that we have done in this slide, as you can see here, the allowable value is 32.31 and the effective depth is 25.92, which means the actual is lesser than the allowable, which means the deflection is okay. Okay, for the cracking part, for our spacing maximum slab and maximum slab for main and secondary bar is okay because the slab that we have obtained for the spacing, which is 225 millimeter from the main bar, and secondary bar, which is 450 millimeter, which means it's okay because it's smaller than the spacing maximum slab. And here is our detailing for our simply supported slab, as you can see here in this slide. So moving on to the two-way slab calculation, as you can see here, the specification mostly we based on the Euro code to solve it and to know the actual value of the specification of our design. As you can see, for example, the characteristic action is for the GK 5.75 kilonewton per meter square and the QK is 3.0 kilonewton per meter square. So for the action that we have obtained the value of the design action, which is 16.65 kilonewton per meter square, the formula that we have obtained in the Euro code. And for the analysis that we have proven that this is two-way slab, which is less than 2, and for the moment of the short span and long span also based in Euro code for the formula, and for the numbering of 0.093 and 0.055, which is also based in Euro code to achieve it or to obtain it, and the value of the short span, which is 18.97 kilonewton meter per meter, and for the long span, which is 11.22 kilonewton meter per meter. By obtaining the formula that we have learned in the previous class, in the structural class, we can able to achieve the effective depth, which is 140 millimeter for the dx, and for the dy, which is 130 millimeter. And from here, we can calculate the short span by using the formula and the given data at the previous value that we have obtained. So for here, we can see the compression reinforcement is not required, and which is okay because it's less than 0.167. So as you can see here, the short span reinforcement area that we have obtained, which is 328 millimeter square per meter, has been used H8/150 335 millimeter square per meter. And for the long span, that is the same thing. We have taken or obtained the value of the MSY, which is previously 11.22 kilonewton meter per meter, and the K that we have gotten is less than 0.167, which is okay, and the compression reinforcement is not required. And for the reinforcement area for this long span that we have obtained, which is 209 millimeter square per meter, and we use H8/200, which is 251 millimeter square per meter. So for the AS minimum and AS maximum that we have obtained the value of 182 millimeter square per meter for the AS maximum. I mean AS minimum, and for the AS maximum, which is 6000 millimeter square per meter. And for the shear, as you can see here in this slide, that we have obtained the value of 28.88 kilonewton per meter. And for the design shear resistance, that based on the formula that we have studied previous during the structure analysis class. Alright, let's continue for the design shear resistance that we have obtained for the VRD, which is okay. Why it's okay? Because the value that we have obtained, which is 29.19 kilonewton, is more than the shear that we have obtained of the VED, and is okay. And for the deflection, which is based on the formula that we have learned in the class. So we'll continue at the next slide, which is achieving the allowable value and the actual value. As we can see here, which is 38.31 for the allowable and the actual is 25. As the actual is smaller than allowable, and this means it's okay. And for the cracking part, is okay because the maximum bar spacing that we have obtained is 350 millimeter, which is less than spacing maximum of the slab, and it's okay. Here are the detailed drawing of the two-way slab. As you can see here, the slab thickness is 125 millimeter and concrete cover is 30 millimeter.
The slide shows that this is a specification about the column. So we use H6 to 140 as our lap joint. This is a detailing about our column.
This is our building quantities based on case flow from foundation, column, beam, slab, door, wall, and so on. After we calculate all the building quantities from our cash flow, the final amount we get is average 320,000 ringgit. That's all for building quantities. That's all for our presentation. Thank you for your time.